The topic of this lecture is important theorems of Riemann integration part 1. We are going to cover these topics in this lecture: theorem number 1, theorem number 2, theorem number 3, and one example. So let us see what is the statement of theorem number 1. Let f is bounded function on closed and bounded interval ab, and sigma and tau be any two subdivision of ab. Then upper sum with respect to sigma of f is always greater than lower sum of f with respect to tau. That is, if we take upper sum with respect to any of the subdivision, that will be always greater than equal to lower sum of f with any other subdivision, that we are going to prove. So let us start the proof. We shall prove the first that if sigma star is any refinement of sigma, we know what is mean by refinement, then upper sum of f with respect to sigma is always greater than upper sum with respect to its refinement. Now, it is enough to prove the case when sigma star, that is the refinement, is obtained from sigma by adding only one point of subdivision. That is, sigma is contained in sigma star, and sigma star contains only one more point than sigma. Okay, so let us see, let us proceed. Let sigma be any component signal. Let sigma have component interval, say I1, I2, In, and sigma star has component intervals, say I1, I2, Ik star, Ik double star, and In. So what we did here, we divide this Ik interval, this Ik, into two parts. The first part is Ik star, and the second part is Ik double star, so that Ik is equal to Ik star plus Ik double star, and length of Ik will be length of Ik star plus length of Ik double star. Now, since Ik star is contained in Ik, this is a subset of this Ik. So so supreme value of f on Ik star will be clearly less than supreme value of f on Ik. Similarly, Ik double star is a subset of Ik. So supreme value of f on Ik double star is less than equal to supreme value of f on Ik, because this is a subset of this. Because of this, when we find the upper sum of f with respect to sigma star, that will be by definition summation j is equal to 1 to n mfij into ij plus mfik star into length of Ik star and mfik double star into length of Ik double star, because we have divided Ik into two intervals. Now that will be less than equal to, because of these two inequalities, we replace these two by mfik, and we take the common mfik from these two, so we get the less than or equal to inequality, and we get this expression, and this expression is nothing but summation j is equal to 1 to n mfij into length of ij, and the sum of these two is simply the length of Ik. But all this complete expression, this expression is nothing but the upper sum of f with respect to sigma. So we have proved that upper sum with respect to sigma star is less than or equal to upper sum with respect to sigma. So this part is proved. Now let us proceed. Similarly, if tau star is any refinement of tau, then we have that lower sum with respect to tau star of f is always greater than lower sum of f with respect to tau. So in this case, the inequality is reversed. Now, if we take sigma union tau, a common refinement of both sigma and tau, then by 1, that is upper sum of f with respect to sigma is greater than upper sum of f with respect to sigma star. And second, that is this inequality, we have upper sum of f with respect to sigma that will be greater than equal to upper sum of f with respect to sigma union tau, because this is the refinement, and this inequality holds that upper sum is always greater than the lower sum, and because of the inequality second, this is the refinement. So lower sum with respect to f with respect to sigma union tau is greater than equal to lower sum of f with respect to tau. So we have the first one and last one. We see this one to this one, we have that upper sum with respect to sigma is always greater than lower sum with respect to tau. Hence, this theorem is proved. Now let us see this remark. This says that upper Riemann integral is always less than the lower Riemann integral is always less than upper Riemann integral that we have seen in the previous lecture. And if sigma is any subdivision of AB, then upper Riemann integral is always less than any upper sum with respect to any subdivision. This you should keep in the mind. Similarly, lower integral of f over AB will be always greater than equal to lower sum of f with respect to any subdivision. These two are important, that will be useful in the next theorem. Now let us see the next theorem. The statement says that let f is bounded function on closed and bounded interval AB, then f is Riemann integrable if and only if for every epsilon greater than 0 there exists subdivision sigma of AB such that upper Riemann sum is less than equal to lower Riemann sum plus epsilon. So we have to prove that if f is Riemann integrable, that is upper Riemann integral is equal to lower Riemann integral if and only if this condition holds. So let us start the proof. Suppose we start supposing that this inequality holds. So suppose for given epsilon greater than 0, there exists a sigma greater than 0 such that uf sigma is less than equal to lf sigma plus epsilon. Then since upper Riemann integral is always less than upper sum, as we have seen in the previous slide, and lower Riemann integral is always greater than the lower sum, so we have that upper Riemann integral is less than equal to upper Riemann sum, that is less than equal to LF sigma plus epsilon because of our this supposition, that is less than equal to lower Riemann integral plus epsilon because of this. But this implies from first and last, from this and this, we have that upper Riemann integral is less than equal to lower Riemann integral plus epsilon. But this epsilon is arbitrary, so we have that upper Riemann integral is less than or equal to lower Riemann integral. But we always have that lower Riemann integral is always less than upper Riemann integral. So because of these two, this and this, we get the inequality that lower Riemann integral is equal to upper Riemann integral, and this implies that f is Riemann integrable. Now let us see the converse part. Suppose that f is Riemann integrable, that is lower Riemann integral is equal to upper Riemann integral. Now by definition, upper Riemann integral is GLB of upper sums and lower Riemann integral is LUB of lower sums, that is by definition. Now let epsilon greater than 0 be given. Then upper Riemann integral with respect to f plus epsilon by 2 is greater than equal to upper Riemann sum, upper Riemann integral of f. So it means that a to b f plus epsilon by 2 is not a lower bound of this set. But this implies we can find a subdivision sigma that upper Riemann integral of f plus epsilon by 2 is greater than upper Riemann sum. Similarly, lower Riemann integral minus epsilon by 2 is less than equal to lower Riemann integral. It means that this lower Riemann integral minus epsilon by 2 is not an upper bound of the set of lower Riemann sums where tau is a subdivision. So we can find a subdivision tau such that this inequality upper lower Riemann integral minus epsilon by 2 is less than lower Riemann sum with respect to tau. So these two things are important here to note. This is the first thing and this is the second thing. Now from these two, we have that lower Riemann sum with respect to tau plus epsilon by 2 is greater than equal to lower Riemann integral with respect to f. That will be upper Riemann integral with respect to x. Why this is so? Because f is Riemann integrable and that is equal greater than upper Riemann sum with respect to sigma minus epsilon by 2. And from this, we obtain by taking first and last over here, this first one and the last one, we get the lower Riemann sum with respect to tau plus epsilon by 2 is greater than upper Riemann sum minus epsilon by 2. Now let us take sigma union tau is a refinement of sigma and tau both, then lower Riemann sum with respect to sigma union tau plus epsilon by 2, that will be greater than equal to lower Riemann sum plus epsilon by 2 that we know, and that is greater than equal to upper Riemann sum minus epsilon by 2. This is from here, and this will be greater than equal to upper Riemann sum with respect to refinement that we have seen in the previous lecture minus epsilon by 2. So from this two, from the first one and the last one, this first one and the last one, we obtain that upper Riemann integral with respect to sigma union tau is less than equal to, because of this strict inequality, less than equal to lower Riemann sum with respect to sigma union tau plus epsilon. Now this sigma union tau we can suppose is a sigma star, a subdivision. So we obtain a subdivision of AB such that upper Riemann sum with respect to sigma star is less than lower Riemann sum with respect to sigma star plus epsilon. So by this way, this theorem is proved. Now let us see one very simple theorem. It says that if f is Riemann integrable over AB, then modulus of f is also Riemann integrable over AB, and modulus of integration of AB of f is less than equal to integration of over AB of modulus f. So this is simple statement that we are going to prove. As f is Riemann integrable on AB, so by definition that f is continuous almost everywhere on AB. This is a one concept that f is Riemann integrable means f is continuous almost everywhere on AB. But this implies, because since modulus of f is also continuous at every point where f is continuous, therefore modulus f is also continuous almost everywhere on AB, and because of this modulus f is Riemann integrable. So concept is simply, because f is Riemann integrable on AB, so f is continuous almost everywhere on AB. Because of this, modulus f is also continuous almost everywhere on AB, but this gives that AB is f modulus f is also Riemann integrable. So that part is over. Now since modulus fx is less than equal to modulus of fx, which is equal to this, for all x belongs to AB, so this inequality hold over here also, that is integration over AB of f is less than equal to integration of AB over modulus of f. This is the first one. Similarly, minus fx is less than equal to modulus of fx, which is equal to this for all x AB. So this inequality hold over here also. So minus of AB over f is less than equal to integration over AB of modulus f. Now because of this any number, we can say this is less than equal to any second number, and minus of that number is also less than the same number. So we have from 1 and 2, the modulus of this is always less than equal to this. So by this way it is proved very easily. Now let us see one example. The show that the converse of the above theorem is not true. For this, consider the function fx is equal to -1 if x belongs to AB intersection Q, that is, if x is rational, lies between A and B, and it is 1 otherwise. In this case, modulus of f is equal to 1, a constant function, and constant function is always Riemann integrable. So modulus of f is Riemann integrable over AB. But f is not continuous almost everywhere because of this definition on AB. So f is not Riemann integrable. So this example shows that converse of the above theorem is not true. So thank you very much. You can find the link of this lecture in the description box. Thank you.